Now, in the previous class, we tried to look at the 6 SPC tools that we can apply in order to solve a problem in regards to quality. So the tools that we first we looked at histogram to see the nature of a process, whether a process is working normally or not. So when you suspect that something is wrong in a process, you could use histogram to identify whether it is operating in a normal operation or not. Then we saw a check sheet. Usually it is used for systematically and consistently collecting data that we could merge as we see it fit, even though it is collected by various people at various time along the process. Then we also saw a cause and effect diagram, where we'd be looking at what are the possible root causes for certain effect. It might be positive or negative effect, but we'll have an effect, or we could say a quality problem or a quality issue, and what possible reasons would cause that effect would be outlined in the cause and effect diagram. Then that cause and effect diagram would be analyzed further in order to see which root causes were actually causing the effect. So drawing the cause and effect diagram is not the end of the analysis, but rather identification of the root causes that are actually affecting the process is the target. Then we have also seen Pareto analysis. Pareto analysis would tell us or would assist us in differentiating the trivial few from, the trivial many from the vital few. So the logic is that 20% of the causes would be responsible for 80% of the effect. So here would be taking a frequency data, but mind you, it's only frequency. Would take the frequency data and see which ones are the high occurring problems. So if we insist, we could associate it with cost of each defect in order to see the magnitude of the effect as well. So the differentiate from the causes or from the issues that we have at our hand is which ones should we focus upon, or for which ones should we give priority could be identified using the Pareto analysis. Then the other tool was a flowchart. In a flowchart, we would identify what is happening in our process so that we could have a good understanding of the process steps, what is happening where, and what are the critical issues in our process. So that is the flowchart. Then finally, we saw the scatter diagram. Scatter diagram would enable us to see the relationship between two variables. The two variables might be two quality characteristics, or quality characteristics and a factor, or two factors influencing a quality characteristics. So when the reason why I use scatter diagram is that we don't want to influence only one variable that may have a negative influence on the overall effect. So we want to be careful whenever we alter some variables or some factors in a process, so that we don't influence the quality characteristics in another dimension. So seeing the relationship between these variables, two variables, would enable us to see how we could positively manipulate our process. Then the seventh tool suggested by or organized by Kaoru Ishikawa is the control chart. Control charts are considered as the central part of statistical process control. As we said previously, in statistical process control, we'll be focusing on the process inputs and what they're actually revealing at the end. So that would be our attention in this class. Now, statistical process control would use these control charts to check production process if any part of the process in some way is not functioning properly. Remember histogram. Now we are looking at histogram from a horizontal perspective. And we're looking at the classes or the subgroups. But here, again, even though we are going to take sample, we are going to see them per sample basis, and would be plotting each of the sample output, the summary of the sample output, in order to see whether the process is functioning normally or there is some sort of problem within the process. So again, just like a histogram, the statistical process control, the control charts they would be used as a means of identifying whether there is a problem in the process or not. And control chart is normally developed by Walter Schwarzert in the 1920s in Bell Laboratories. And initially, there were some weaknesses in the control chart that was developed by Schwarzert, but Deming again associated the control chart developed by Schwarzert to his theory of variation. Deming emphasized that we need to reduce variation between our products. And in order to reduce variation between our products, we could use control charts that were developed by Schwarzert. That was the logic that Deming followed, and it is widely accepted. So the basic principle that we are going to follow is eventually, or in a general sense, we want to eliminate or minimize variability. If you take two products, for example, if you purchase a Lexipen, two Lexipens, when you look at them, they would be identical, or they would seem identical, but they are not actually identical. There is nothing identical in this world. What matters is your level of measurement. So in SPC, we acknowledge that there is always variability in our production process, and there would be variation between two products, two similar products. Now the question is, how deep are you willing to dig in order to find the level of variability? So a process that is operating in a normal operation, it would have certain variation between the product outputs. And we call those variations chance or random variations. And these are apparent almost in everything. For example, if we say that a shaft is supposed to be 10 centimeter, then if you have two shafts who are measured to be 10 centimeter, it doesn't mean that they are identical. They might be the same, but they are not identical. What matters, as I said previously, is your level of measurement. If you measure them in centimeters, then they might be the same. If you measure them in millimeter, then you might see some difference. If you measure them with micrometers, then you'd see a lot of difference. If you measure it with nanometer, then you'd see a lot of variation. Okay, so there is always variation, but the variation that would occur naturally and that would not significantly affect our intention is known as chance or random variation. For example, as long as our intention is 10 centimeters, we might not be interested in a deviation of 1 millimeter or 2 millimeter up to 5 millimeter, let's say. We might say it's okay, because our intention is that it should be 10 centimeter. Our measurement is of larger scale. But when we actually go through the cutting operation, there might be certain vibration from the machine, which would be okay with us as long as our measurement is in centimeter, or our intention is to get a precision under a centimeter measurement. Or there might be humidity or heat that would expand the material that's going to be cut. That would not really significantly affect our intention. So these type of variations are okay, or are random, and we are not really worried about them. There is a natural elasticity of the product itself. or there might be a truck passing by, which would cause additional vibration. So these are random and chance variations, which are said to be observed in a process, and in statistical terms, they are normal. There is always variation, and we would statistically would accept this type of variation as they will not persist and influence our target. The other type of variation is a variation that would be caused by a specific assignable reason, and that reason would significantly impact our intention. For example, if we are interested to obtain the 10 centimeter dimension shaft, but our measurement instrument has a defect or an issue of consistency, then we'll not be able to actually measure and cut the product properly. So if there is a problem with your measurement instrument, then that would be an assignable cause for the variation that would arise. Or if the operator does not really take care in measuring the instrument, measuring the part to be cut, then we might have variation. For example, if they are negligent, they might not even take the proper measurement instrument to measure what is going to be cut, but rather they would just estimate and cut it. Or they will not place the meter or the measurement instrument properly. They might incline it, or they might do it in a negligent way that would result in a dimension of maybe 9 centimeter or 11 centimeter or whatever. So these type of variations, we can say that this is an assignable variation. The worker is making the variation, or the worker is the reason for the variation that we are observing in the process. Or we could say the measurement instrument is the problem that is causing variation in our products. Or if the material itself is not really a material that we cut with that precision, if it is a material that would fracture, then we can say that the material is the reason why we are not getting, we are getting too much variation between our products. So if you could assign the variation to a specific thing, then we could say that this type of variation is an assignable variation. So basically, we have two types of variability, or we have two types of variation. The first ones are those occurring naturally. We call them chance or random variation. And the second one are the assignable variations, where we could identify who or what is causing the variation. And we could eliminate it. That is the most important part. We could eliminate the assignable variations, but it is maybe impossible or too expensive to eliminate chance or random variations that we mentioned initially. So the concern of control charts is to identify whether in a process do we have assignable variations, or are the variations natural variations or random variations that we could ignore. There would be variation, that is understood, but is the variation natural or something random that we could easily ignore, or is it something that we need to be concerned about? If it is an assignable variation, then we need to be concerned, and we need to identify what is causing that assignable variation. So control chart would assist us in graphically displaying the quality characteristics that has been measured or computed from a sample versus sample number of the item. So we have different elements of a control chart. The first one is the data points. Now, these data points that you see here, each of these would represent a subgroup or a sample. In a sample, you have multiple measurements, okay? This is not a single value, but rather you may have a series data points. They would be merged together as one sample. Sample 1, sample 2, sample 3, and so on. So these are the ones that would be telling us the variability within the process that is producing these outputs. Then the other points are the center line, the upper control limit and the lower control limit. These points, the center line, the upper control limit, and the lower control limit, they are computed from the aggregated evaluation of these sample points. The sample data points are merged together and analyzed in certain perspective in order to identify the center line, the upper control limit, and the lower control limit. So these are derived from the process itself. Please take a note of this. Then when we see what we are going to do, remember the process approach that we have enlisted in the first chapter. So you have an input, you have a process, and you have an output. From the output, you are going to have a measurement. You might even take a measurement from the input. And the first thing that you do is you plot this graph and identify whether there is an assignable cause or not. If there is an assignable cause, then you should follow the loop. If there is nothing, then the process would go on as it is. But whenever you detect an assignable cause, then you identify the root cause of the problem. Then you implement corrective action for the root cause, verify whether the problem is solved. If it is solved, then the process will continue, and we would make sure that the process is working under a normal condition. So we say that in general terms, we'll go to the details of the rules later on, but in general terms, as long as you don't have any point below the lower control limit or above the upper control limit, we say that a process is working normally. But normally, since we are talking about statistical analysis, then this is going to be divided into 3 segments or 3 warning levels. And the 3 warning levels, they would be divided like this. This would be, so you have 3 zones, A, B, and C. The same goes for this one. So this would be divided into 3. So you have A, B, C. And when you look at the output, it is an inverted normal distribution curve. Sorry. Debate article. Anyways, this is supposed to be an inverted normal distribution, like this, something like this at least. Is it normal distribution? No, a normal distribution. ባለፈው class ላይ ስናይ እንደነበረው it should be divided. It would be divided into sigma levels. Now this would be the center line. Then this would be the sigma level would be divided into sigma 1, sigma 2, and sigma 3. In the negative side as well, you have sigma 1, you have sigma 2 or 2 standard deviation, and sigma 3 or 3 standard deviation. So these are the regions that we are talking about. We'll look at them later on. That you could invert this one 90 degree and have a look at the distribution of these data points along the center line. So why do we use this control chart? Most processes do not operate in a state of statistical control. That means the routine and attentive use of control chart would identify any assignable cause whenever they arise. So you are under a normal operation, and whenever there is a deviation, if you use control charts properly for monitoring your operation, you could identify whenever there is an assignable cause. If there is an unassignable cause, you need to take corrective action right away in order to bring the process under normal control. እየሰራ ልክ ችግር ሲኖርበት ችግሩን ቶሎ አይደንቲፋይ አድርጋችሁ ወደ ኖርማል ኦፕሬሽን መመለስ እንድትችሉ ማለት ነው። That is what we mean by control. You identify a problem, you go for identification of the root cause, you take corrective action, and you bring it to the normal operation. The normal operation would be when you have a normal distribution here. Or for ease of understanding, we would identify whether there is a point beyond the control limits or other things that we could measure. We'll come to that later on. So in order to identify this assignable cause of variation, the control charts would be very instrumental. If the assignable causes can be eliminated from the process, you can be sure that variability would be reduced. And when we say variability, we are not talking about the natural variability, but rather we are talking about the assignable variability. A variability that is caused by something that you can eliminate if you take corrective action. And the control chart is used only to detect the assignable cause of variation. This is very important. Okay, when you find an assignable variation, then it is telling you that you need to initiate an out of control action plan for your process. The out of control action plan would be something like this. Okay, when you measure and analyze the control chart here, the control chart would be used here. So when you use the control chart and identify that there is a point, for example, here, let's say the next point is out here. Okay, so when you look at this, sorry, when you look at this, then it is telling you that you need to initiate an out of control corrective action. So you initiate this out of control corrective action plan in order to detect the assignable cause. So what is causing this variation? Is it the operator? Is it the material? Is it the machine? Is it the measurement instrument, or what? So you identify the root cause and eliminate what is causing it. For example, if the operator needs training, then you train the employee. You train the employee and see the process output. If it is okay, then you can go on with your natural process. So the control chart is only used to detect whenever there is an assignable variation. Identification and rectification and elimination of the root cause is initiated or conducted by an out of control action plan, which is known as the control mechanism for any process. So you need to have this control mechanism or out of control action plan. So as I said previously, each of these data points in the graph, they're extracted from a sample. So that is known as subgroup or samples. So the rational subgrouping is very, very important. Now, what we mean by this is that, for example, you have sample 1, sample 2, sample 3, and so on. Or you could also call them subgroups. And each of these subgroups, for example, let's say they have 5 samples. Okay, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. Okay. Sorry. Again, for example, for the third sample, you have 31, 32, and so on. 32, 3, 3, and so on. So now you could fill out the rest. Now, what we mean by the rational subgrouping is that we want to have these samples to have high level of similarity. That means we want them to be collected, for example, from the same operator at the same operating time, using the same machine, using the same instrument, and so on. So that the samples, these ones normally, we call these ones observations. Okay? እነዚህን observation ነው የምንላቸው እያንዳንዱ ማለት ነው። So you have sample 1 and 5 observations. So the observations within a sample need to have high percentage of similarity. Okay? Then the subgroups need to differentiate, or the samples need to differentiate something about the process uniquely. So the issue of rational subgrouping is that we want to maximize the similarity between the observations within the sample and maximize the difference between the subgroups or the samples. We're talking about the same process, but we want to maximize the difference between the samples and minimize the difference between the observations within a sample. So subgroups or samples should be selected so that if assignable causes are present, this is our intention. We want to identify the assignable cause of variation. So if there is an assignable cause of variation, then the chance for difference between the subgroups would be maximized. That means the difference between these subgroups would be maximized so that we could identify for the occurrence of this point, for example, or this point, or this point, or for each of the sample point, then the difference is big, or you could see the difference between these operations. That means you could see the difference on who was the operator, what type of raw material was used, which machine was used, and so on. Whereas within the subgroup, we want to minimize the difference because when we say this point is out of control, for example, we say this point is out of control. So we want to identify who was the operator, what machine was used, which type of raw material was used, which type of instrument testing equipment was used, and so on. So if the inputs are similar, then the observations, the difference between the observations within a single sample would be minimized. So it would give us an opportunity to identify what was the cause. Okay, so in subgrouping, we want to maximize the difference between subgroups and minimize the difference between the observations as an input. Then in constructing this rational subgroup in a sample and process አለ ከሶስት ሳምፕል እንውሰድ ስንል rational subgrouping ያስፈልገናል ነው ያን subgrouping እንዴት እንስራ ስንል you could use this as a tool as a tip. For example, you could select consecutive units of production. Consecutive production. This would provide a snapshot of the process. So for example, you could start early at the morning. አንድ ፕሮሰስን ጠዋት ላይ እንወስዳለን ጠዋት ልክ ስራ ሲጀምር ሰራተኛው ከሰዓት ደግሞ ልክ ከምሳ ልክ ሲመለሱ እንጀምራለን የሚቀጥለው ሽፍትም ልክ ሲጀምር እንወስዳለን ከረፍት ሲመለሱ እንወስዳለን ስለዚህ ምንድነው የሚነግረን ኮንሲኩቲቭሊ ልክ ሲጀመሩ ከረፍት ሲመለሱ ያለውን ስናፕሾት ይነግረናል. So this is one approach and this is good to detect the process shift. ፕሮሰሱ በየሰዓቱ ጠዋት ከሰዓት ሽፍት ሲጀምር እና ከረፍት በኋላ በእያንዳንዱ ሽፍት ያለውን ፕሮሰስ ሽፍት ይነግረናል ፕሮሰሱ እንዴት ሽፍት እያደረገ ነው የሚለውን ማለት ነው. The other is you could select a random sample over the entire sampling interval. እዚህ ለምሳሌ በቀን ውስጥ 3 ሽፍት አለ. So you could take the sample from the 3 shifts የጠዋት የከሰዓትና የማታ ሽፍት ሊኖረን ይችላል. So you could take the samples from these 3 shifts, but your sampling would be totally random. That means you could take the sample at any time in any of the shifts. ስለዚህ ጠዋት ላይ ግዴታ ሲገቡ አይደለም 3 ሰዓት ላይ ልትወስዱ ትችላላችሁ 5 ሰዓት ላይ ልትወስዱ ትችላላችሁ 9 ሰዓት ልትወስዱ ትችላላችሁ. So you are making the data collection random but within certain groups. That means the 3 shifts of the day. So, and this is good at detecting if the mean has shifted in the shifts themselves. That means ጠዋት ላይ ሲሰራ or ከረፍት በኋላ ሲሰራ እያልን ሳይሆን at any time collect የተደረገ ነው. ስለዚህ ሚኑ shift ያደርጋል ወይስ አያደርግም የሚለውን ለመረዳት ያስችለናል ማለት ነው. So these are just 2 tips in order to have rational subgroup. Either you could collect consecutive units of from the production, or you could take random sample over a certain period interval. ስለዚህ አሁን ለምሳሌ 5 ነው የምንወስደው ካለን ጠዋት ልክ 2 ሰዓት ላይ 5 ሳምፕል ትወስዳላችሁ ማለት ነው። እዚህ ከሰዓትም ትመጡና ከሰዓት ደግሞ let's say 8 ሰዓት ላይ የሚገባ shift አለ የሱን ደግሞ እንደገና 5 ሳምፕል ትወስዳላችሁ ልክ 2 ሰዓት ላይ ትወስዳላችሁ ይሄን ደግሞ 8 ሰዓት ላይ አምስቱን በተከታታይ ትወስዳላችሁ ማታ ደግሞ maybe ማታ 2 ሰዓት ላይ ሄዳችሁ እንደገና 5 ትወስዳላችሁ and so እዚህ ጋር ግን ስንመጣ shift የሚጀምረው 2 ሰዓት 8 ሰዓት እና እንደገና ማታ 2 ሰዓት ነው ግን ከ2 ሰዓት እስከ 7 or 7:59 ድረስ ኤኒ ታይም መጣችሁ 5 ልትወስዱ ትችላላችሁ randomly ይሄን ደግሞ ከ8 እስከ 1 ሰዓት ማታ ኤኒ ታይም መጣችሁ ልትወስዱ ትችላላችሁ 5 so this is you're taking it randomly throughout the sampling interval but here you'd be collecting it at certain point and you'd be collecting it consecutively so this would give you certain rational subgrouping በእነዚህ shift ያሉትን ዲቪዬሽኖች ለመረዳት በደንብ ያስችላችኋል ማለት ነው so let's go on and see the design of control charts and how they're applied now suppose we have a process that produces piston rings and the process mean of the ring diameter is 74 millimeter so this is the process mean that means this is not the specification okay specifications are normally indicated by T as for target value but when it is mu then it is the process mean from the process that is producing the piston rings then we take the average value of the diameter of the rings and this average value is 74 millimeter and the process standard deviation again from the process output you'd be collecting the standard deviation so remember you need to go back and revise your standard deviation calculation you'd identify the mean ካላችሁ process output ውስጥ mean ትፈልጋላችሁ the difference between the mean and each of these observation would be identified and squared this would be summed together and put under square root and divided by the number of samples or n minus 1 minus n minus 1 n where n being the number of samples so you could go back and revise the formula for standard deviation so once you identify the standard deviation for example here it is 0.1 standard deviation is designated by sigma and that sigma for the process again for this process is 0.1 so the sample each of the samples let me take you back again here for example this is one sample and we have 5 observations so the sample size is known as 5 because we have 5 observations so similarly here sorry sample of size 5 are taken giving a standard deviation of the sample average as the sample this is the standard deviation of the process now standard deviation of the sample average would be the standard deviation divided by square root of the sample size or the sample size the number of observation in a sample so you'd have this sigma x or standard deviation of the sample average and you'd use this in order to identify the 3 elements of the control charts as you said previously and normally what is recommended in general terms is to use 3 standard deviation ቅድም የሰራውላችሁ ጋር መልሳችሁና 3 standard deviation ማለት 1 2 3 እዚህ ጋር አለ so እዚህ ጋር ደግሞ 1 2 3 አለ so this would be plus or minus 3 standard deviation so each of these dimension each of this width is designated by sigma and plus or minus would tell us this is the minus side and this is the plus side so this would be what we call the 3 sigma and this would account to 99.7% of your observations in a sample so what is normally recommended in control chart is to be set at least at 3 standard deviation አንዳንድ ጊዜ እንደ ሁኔታው 2 standard deviation ልንጠቀም እንችላለን that means ከዚህ ጀምረን ከዚህ እስከዚህ ብቻ ያለው ነው ኮንሲደር የምናደርገው ማለት ነው so this would be 2 sigma. But in this case, you'd be regarding many data points as invalid, or you'd be discarding many values. And this is not really recommended. So for us, we'd be considering a 3 sigma standard deviation level. So control limits can be set at, should be set usually, not always, but in most cases, they should be set at 3 standard deviation from the mean in both direction, that means plus or minus. So the 6 sigma control limit would be computed as the upper control limit plus the mean value, or mu, the process mean, okay, that we have seen here previously, 74 millimeter, plus or minus. The plus would be for the upper control limit, and the minus would be for the lower control limit. 3 would be the standard deviation that we discussed previously, and this one would be the sigma for process average that we discussed, that we indicated previously. So you could use this in order to identify the upper control limit, the lower control limit, and the center line. The center line would be the process mean. Now you could use this and plot the graph, okay? Now this is just for illustration. So you have the center line at 74 millimeter, and the upper control limit would be a bit higher than that. So it would be 74.0135, and the lower control limit would be 73.9865. So you could see, since we have taken 3 standard deviation for both, but plus or minus, so the difference between the center line and the upper control limit and the center line and the lower control limit would be the same. The absolute value of the dimension would be the same. So this is normally how you would construct a control chart. We'll go in depth into the details, but this is how you construct. You take the process mean ለማውጣት ያሏችሁን ፕሮሰስ በሙሉ ወስዳችሁ የእያንዳንዱን ሳምፕል አቨሬጅ ወስዳችሁ ከዛ በኋላ ደግሞ ሁሉንም ሳምፕሎች ደግሞ አቨሬጅ አጠቃላይ ስትወስዱ ፕሮሰስ ሚኑን ታገኛላችሁ። You could easily identify the sample size, በእያንዳንዱ ሳምፕል ውስጥ ስንት ኦብዘርቬሽን አለን የሚለውን በማየት ማለት ነው። You could calculate the standard deviation from the process output, እያንዳንዱን ቫልዩ ከሚን ቫልዩ ዲፍረንስ እየወሰዳችሁ ስኩዌርድ እያደረጋችሁ በስኩዌር ሩት ውስጥ አስቀምጣችሁ ያው የስታንዳርድ ዲቪዬሽን ፎርሙላ በመጠቀም ማለት ነው። You could identify the standard deviation for the process, and you could use the process sample size in order to identify the standard deviation of the sample average. Then እነዚህን ተጠቅማችሁ እነዚህ ሶስቱ ክሪቲካል ሴንተር ሊሚቶችን ማውጣት ትችላላችሁ። The center line, or the central line, the upper control limit and the lower control limit, and you could use the sample average to plot these values easily ማለት ነው። በኋላ እያንዳንዱን ክላሲፊኬሽን ስንመጣ ደግሞ የበለጠ እያብራራን ነው እንሄዳለን። Now normally, as I said previously, what we are looking for is a point beyond the upper or the lower control limit. Okay, so if you find a point that is, for example, the next point, if it is in here, then you could say that this is out of control, and you need to identify the reason for this out of control situation. That would be basically the analysis for the assignable cause of variation. እቺ እንደዚህ አይነት ፖይንት አለች ማለት assignable cause አለ ማለት ነው። እዚህ ያን ምክንያት ወደ መፈለግ እንሄዳለን ማለት ነው። But control charts, they are not only used to identify the root cause of the problem, they are also used as a monitoring tool. ይሄ ለኮንትሮል ፐርፐዝ ነው። ኮንትሮል ማለት አንድ ችግር ሲኖር ኮሬክቲቭ አክሽን ለመውሰድ እንዲያስችላል። እዚህ ጋር አውት ኦፍ ኮንትሮል ነው ስንል ኮሬክቲቭ አክሽን ለመውሰድ ያስችላል። But in a process monitoring phase, you're going to use it continuously, and that would demand further analysis as well. So a process is considered to be out of control if any of the following points occur in monitoring phase. ሁለት ፌዞችን በኋላ የምናያቸው ሆነው ማለት ነው። So if you have one point outside the 3 sigma control limit, then we say it is out of control. ይሄ 3 sigma እነዚህ ፖይንቶች 3 sigma ሌቭል ናቸው ብለናል። እዚህ ከነዚህ ውጭ አንድ ፖይንት ካለ directly we say that it is out of control. out of control ምንለው መቼ ነው ነው። እዚህ የመጀመሪያው አንድ ፖይንት ከዚህ 3 ሲግማ ሌቭል ውጭ ሲሆን ነው። ሌላኛው ደግሞ 2 out of 3 consecutive points plot beyond the 2 sigma warning limits, or 3 when we have 4 out of 5 consecutive points are plotted outside at a distance of 1 sigma or beyond the center line. ከአምስቱ አራቱ ማለት ነው። እዚህ ጋር ከሶስቱ ሁለቱ እያለ ነው። ወይም ደግሞ 8 consecutive ፖይንቶች በአንድ ሳይድ የሚሆኑ ከሆነ ከሴንተር ላይኑ then we call that out of control. Or if we have 8 observations that would demonstrate certain run, ሁሉም ቀጥታ consecutively 8 ፖይንት ወደ ላይ ወይ ደግሞ 8 ፖይንት ወደ ታች የሚወርዱ ከሆነ then that's not natural. አሁንም ቅድም ያልኳችሁ ጋር ነው መልሳችሁ። we are talking about the natural occurrence of a process. So if these things occur, if all these things occur, statistically we don't consider it as being in statistical control. So what do we mean by each of this? Let's have a look at them. For example, if this is the center line በደንብ እንዲታያችሁ ላስምረው. This is the center line and you have the limits here. Okay? Now, if you have 1 point above the upper control limit or 1 point below the control limit, then we say this is out of control. The second one is if you have from 3 consecutive points. Now here you have 1, 2, 3 consecutive points. So 2 out of the 3 consecutive points are above the 2 sigma level. This is the 2 sigma. This is 1 sigma. This is 2 sigma. And this is 3 sigma. So if out of the 3 consecutive points, if 2 of them are above the 2 sigma level, then we say this is out of control. And if you look at this one, you have 5 consecutive points, but out of these 5 consecutive points, if 4 of them are above the first sigma warning line, then we also consider that this is out of control. The same applies to the lower control region as well. So if 3 out of the 3 consecutive points, if 2 of them are below the -2 sigma warning line, then this is out of control. And if 4 consecutive, just like this one, if 4 consecutive points are below the first sigma warning level, then we consider it as a warning or a sign of out of control situation. Or when you look at this, 8 of the data points from the samples are above the control limit consecutively. So 1, 2, 3, 4, 5, 6, 7. No, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now here there are 9. So 9 of the points are above the center line consecutively. So this is not normal. The same applies for a point below the center line. So these situations, this one, like this one, these are considered to be out of control in a monitoring phase. Okay, here we have the trial run. In the trial run, we'll be focusing on such points like this one. Okay, but in monitoring phase, we'll be considering all these points. So all these points would be considered in a monitoring phase. And the other one is when you have this cyclic nature. ዝም ብሎ ይጨምራል ይወርዳል ይጨምራል ይወርዳል. So you can predict this. የሚቀጥለው እንደዚህ እያለ እንደሚሄድ predict ማድረግ ትችላላችሁ ማለት ነው. If you can predict it, then we don't say that it is statistically natural. So these things are the ones that we are going to look for. Initially, we'll be looking for a point that is out of the upper or the lower control limit. But after that, in a monitoring phase, we'll be using all above this Western Electric handbook rules in order to identify whether a process is working normally under statistical control or not. So let's see the two phases, or before that, let's look at the two types of error in control charts. Now there are basically statistics ላይ ሁልጊዜም ቢሆን error እንዳለ አትርሱ. We acknowledge we are using numbers and there would be certain level of error. You have to acknowledge that. So in control chart as well, there are two types of errors. So as you move away from the center line, there are two types of errors. The first one is the error 1, which is a risk of a point falling beyond the control limits, indicating an out of control condition. Now, for example, here, this is indicating it is beyond the control limits, or this one. And we can say that there is an assignable cause of variation. The process is out of control, and we need to identify an assignable cause of variation for that. But in reality, you may not be able to find any cause for that variation. ነው ብለን ነው የምንነሳው ስታቲስቲካሊ አንድ ፖይንት ከዚህ ከወጣ ከነዚህ ከኮንትሮል ሊሚቶቹ ካለፈ then there is an assignable cause ብለን ነው ኮንክሉድ የምናደርገው የሚቀጥለው ስቴፕ ምንድነው ያ ሩት ኮዝ የሚለውን አይደንቲፋይ ማድረግ ነው but in reality you may not find an associated assignable cause of variation for that specific point ለምሳሌ ዴታ ፖይንቱን ወስዳችሁ ስታዩ ይችኛው ፖይንት ኦፕሬተሩ እገሌ ነበረ ታይሙ ይሄ ነበረ የተጠቀመው ማሽን እነዚህ ነበረ ኢንፑቶቹ እነዚህ ነበሩ ሁሉም ዲቴል አያችሁ በደንብ ኤግዛማይን አደረጋችሁ ግን ከኖርማል ኦፕሬሽን ምንም ዲቤት ያደረገ ነገር ላታገኙ ትችላላችሁ you have to dig very deep of course in that case if you dig deeper and deeper but still you could not find any assignable cause then would classify it as type 1 error okay እዚህ ኮንትሮል ሊሚቱ በጠበበ ቁጥር እንደዚህ አይነት ኤረሮች ሊያጋጥሙን ይችላሉ so you have to be careful the second one is type 2 error where this is the risk of a point falling between the control limits when the process is entirely out of control so you might see that let me take you back so just forget about this one but everything is under control it is within the control limits and you don't see any of the Western Electric handbook rule visibly you might be in such situation but in reality there might be points that were supposed to be out of control for example this point there is an assignable cause or the material used in this case were not as per the standard and they're causing too much defect so you could see that there is something wrong but when you plot it then the process is within control in that case we say this is a type 2 error this is a risk of a point falling between the control limits within the upper and the control limits but the process is actually out of control so the reason for this would be widening the control limits በጣም ስታሰፉት ማለት ነው ለምሳሌ ይሄኛው in reality control ሊሚቶቹ እንደዚህ መጥረፍ ከነበረባቸው then you could see that at least 2 of the points were supposed to be out of the control limit እዚህ ቅድም ሲግማ ሌቭሉም እዚህ ጋር ማተር ያደርጋል ሲግማ ሌቭላችሁን ማጥበባችሁ ማስፋታችሁ 3 ነው 2 ነው 1 ነው ወይ 4 ነው የምትጠቀሙት so all these things would matter on the occurrence of these errors type 1 or type 2 errors but popularly as I said previously would use the 3 sigma control limits and this would give us a higher control over our errors so this is chosen or the 3 sigma control limit is chosen in order to provide a rational to minimum economic loss okay with 99.73% confidence level a confidence level የሚነግረን ምንድነው የፕሮሰሳችንን 99.73%ን ካፕቸር ማድረግ እንችላለን if we use 3 sigma 2 sigma የምትሉ ከሆነ ግን ብዙ ፖይንቶች ላትይዟቸው ነው so that would have its own impact on these errors so it's good to note of these two errors in a control chart. Now let's go back and see the type of errors the type of control chart that we could construct. ምን አይነት ቻርቶችን መስራት እንችላለን የሚለውን እኔ ታደሰ the common definition of quality is exceeding customer expectation through reducing the variation at all. Yes, control chart is the basic tool for reducing variation for assignable cause of variation, but how we can use control chart for non-quantifiable observations? Those cannot be measured in terms of, or is there good? Normally, ጥሩ ሰዓት ላይ እንዳነሳው አሁን እንግዲህ measure non-quantifiable observations የምትለን measure የማይደረጉትን ነው እያወራን ያለ ነው። so measure የማይደረጉ